Okay, this video we're going to be talking about the conjugate root theorem, which is kind of a really important thing in complex numbers. We're going to be talking about it for one or two videos. First thing, before we get into the conjugate root theorem, we have to talk about the fundamental theorem of algebra, which is kind of a complicated way of saying it's actually quite easy. Just ax to the power of 5 plus bx to the power of 4 plus c x cubed plus dx squared plus ex plus f, or whatever you want. So that's just a polynomial, say, so anything with x squared, x cubed, or whatever, of degree 5, because the highest power in it is x to the power of 5, and all the fundamental theorem of algebra says is that this is going to have 5 roots, okay, which means, yeah, you're going to have 5 solutions. So if you want to try and solve this, you're going to get x is equal to 1, 2, 3, 4, and 5, for example. It won't be those numbers, but there's going to be 5 answers. It basically says for any polynomial, as long as like that one with the highest degree, or the highest degree in the polynomial, so the highest power, it's going to have that many roots. So that's all it says. It's not nothing too difficult. Just that'll be important when we're solving questions with the conjugate root theorem. Okay. Next, I'll go to the conjugate root theorem, and how am I going to do this? Okay, give me 1 second. Okay. Hopefully that worked there, yeah? So this is what the conjugate root theorem says. So I'll go through each bit, don't worry. So the conjugate root theorem, let me get the pen back out. Yep. The conjugate root theorem says that if z is equal to a plus bi is a root of a polynomial, so remember this is just any kind of polynomial, with real coefficients. So the real coefficients means that a, b, c, d, e, and so on, they're all real. There's no I, it could be ci x cubed. So there's no, as long as there's none of those, then the conjugate root theorem stands. Okay, and most polynomials we've seen so far don't have an I as a coefficient. Okay, so it's true for most polynomials. Okay, so again, if z is equal to a plus bi as a root, then z conjugate, so I couldn't do the bar, but I'm just going to draw it in here. So that's not underlining the g, that should be over the z. Then z conjugate, which is a minus bi, so remember the conjugate is always the complex part, changing the sign in front of it, is also a root. Okay, so we're looking at an example, and hopefully that'll clear it up. But this is that's what the theorem says basically. Okay, we'll go blue. Our example is going to be example 1. It's only going to be one example. So z is equal to 4 plus 3i. We'll say is a root of f of z is equal to z squared minus 8z plus 25. Okay, so this is our quadratic, and we know that z is equal to 4 plus 3i is a root of this. Okay, so the conjugate root theorem will tell us that z is equal to, or z bar is equal to 4 minus 3i is also a root. Yeah? And that's all it says, okay? But it's still really helpful. It means we can get the other one, and it becomes way more helpful when we have something like this above to the power of 5. So we can get 2 of the roots really easily, or we can get the second root easily if we have the first one, okay? So, but there's this question here, so I'm not going to write it out, but it's asking us to prove this. So we know it's a root, but they just want to prove it just for the sake of the question, okay? So if we want to prove that something's a root, do you remember back to, it'd be the video on cubic equations. Basically, if you want to prove that something's a root, you have to sub the root into here, or into all of these z's, and it should be equal to 0, and that means that number is a root. So we're just going to go ahead and do this, okay? So f of 4 minus 3i is going to be equal to 4 minus 3i squared minus 8 by 4 minus 3i, so that should be bracket, plus 25. Okay, so we need to find all of this, and if it's equal to 0, then that means that this is a root, and we've just proved the conjugate root theorem. Okay, so go ahead and do this. Okay, it's going to be 16, because it's going to be 4 by 4, and then, actually, no, I'm just going to do the whole thing out slowly, instead of trying to do it in my head. It'll just be a bit more clear. So, 4 minus 3i and 4 minus 3i, so that's going to be squared, minus, I'm going to multiply this one out now, minus 32 plus 24i, okay, and then plus 25. So it's minus 8 by each term here, and now we're just going to need to work this one out. It's going to be 16 minus 12i minus 12i. So first it's 4 by 4 is 16, 4 by minus 3i is going to be minus 12i, then minus 3i by 4 is going to be minus 12i, and minus 3i by minus 3 is going to be plus 9i squared, and then all of this here, so minus 32 plus 24i plus 25, okay? And a second here. Okay, we're going to put the i's with the i's and the real numbers with the real numbers. So first we're going to have, I'm going to do this in blue, minus 12i, and plus 24i. So that's going to cancel, because minus 12 and minus 12 is going to be minus 24, and this is plus 24i. So I'm going to just draw the lines for all of those. I'll go 16 minus 32 plus 25. So 16 minus 32 is going to be minus 16. Okay, and then plus 25 is going to give us plus 9. Okay, and I'll write them all out just to make sure. 16 minus 32 plus 25 and then plus 9i squared. Okay, so that's going to give us plus 9. Okay, all of this, and then this plus 9i squared. So remember, I squared is equal to minus 1. So 9i squared is going to be minus 9, and this gives us 0. Okay, so we've just proved that the conjugate is also a root of a quadratic. Okay, so we've proved the conjugate root theorem for this question here. Okay, and we'll see you next time.